Here's another video to the lecture Intro PDE. In this video we present the first half of section 2.4. So we introduce distributions. Distributions are generalized functions. So the main idea is that instead of a function we describe a linear map. So instead of function f, or we describe a function f by a linear map. Okay, first we have to introduce this space of functions. C infinity 0 omega, this is the space of real valued smooth functions on omega subset from Rn with compact support in omega. Okay, here the support of a function and we denote this by sub f of a function is the closure of all points x such that f on x is not 0. For a function on omega, this is of course we build a closure in omega. And compact support means that the support is a compact subset of omega. Okay, compact support in omega means support f is compact subset of omega. Okay, these are nice functions, smooth and compact support. Okay, and then for every function f in L1 of omega and any phi which is such a function with compact support, so 0 infinity omega, integral of f phi f phi d mu is well defined and finite. So f element L1 of omega defines a map C to R, which maps phi to integral f phi d mu. This map is linear. And we have, of course, that if we take the supremum norm, integral f phi d mu, absolute value, we can estimate by the L1 norm, the L1 norm here times the supremum norm yeah, where phi supremum is just the supremum of x of omega phi of x absolute value. Okay, so this means that this map is in a specific sense continuous. Yeah, and now the main idea of distributions is that instead of the function f, we use take the linear map as the definition of the function f. Yeah, this is the main idea of distributions. Okay. One question is, yeah, does these linear maps describe f unically? Okay, and this question we will see, we will answer this affirmative. Yeah, in a specific sense we will see this is true. We shall see that this is in a specific sense true. So we can indeed use these maps as description of functions, these linear maps. So generalized functions are such maps. Now, of course, we are interested in differentiable functions. So, can we differentiate the functions described by these linear maps? To decide this, let us assume f is differentiable. Or even a little bit more, let's say continuously differentiable. Continuously differentiable. Okay. By integration by parts, we have the following. Yeah. You remember, integration by parts we introduced by using Gauss at the divergence theory. Okay. So we have dA f phi d mu, by the divergence theory, omega, is equal to integral over f phi times ni, this is the outer normal, over d omega. For omega as in the Gauss sphere. Okay, and since this has compact support, this vanishes. So this is 0. Now dIf phi is, of course, by the Leibniz rule, dF phi plus f di phi. This is Leibniz rule. So we obtain omega dIf phi d mu is just equal to omega minus f di phi d mu. And so we define as the derivative di of such a linear map so we have this linear map, phi maps to f of phi, and now we define dIf by this formula. This is just minus, this minus comes from this integration by parts, f of di phi. And for phi in C0 infinity of omega, di phi is also. So this dIf is well defined and linear. Since phi going to di phi is linear. Okay, so we can in fact differentiate this. We can differentiate this, that in case our linear map corresponds to a differentiable function, then this defines the derivative. And of course we can repeat this. So these generalized functions have infinitely many derivatives. Okay, now there's still something missing. What is missing? Now we give the definition. Also, in order to avoid abstract nonsense, we should impose some continuity of the linear map. So we need some topology. Yes, so we endow with some topology. Unfortunately, yeah, there does not exist a norm which makes C0 omega to a Banach space. Yeah, for this reason, we have to work with Fréchet spaces. We need instead we use a family of semi-norms. Okay, and this family of semi-norms, these are the following expressions. So C0 infinity of omega maps to R plus or R, and phi is just mapped to this norm. We define this as the supremum of K of phi absolute value. Also here K is a compact subset of omega, and alpha is a multi-index. Yeah, and so we assume that this map is continuous with this family of semi-norms. Yeah. These are semi-norms. So this means norms which are not necessarily positive definite. Yeah, so the semi-norms are norms, but we do not assume that if the norm is 0, then the function is 0. Yeah, this is the definition of semi-norms. Semi-norms. Okay. Yeah, and clearly these are semi-norms. Yeah, okay, here you see polynomials of order less than the length of the multi-index. They vanish. Yeah, and if the functions have support in the complement of K, yeah, then these norms also vanish. Okay, now we define here the space of distributions, and we call this d prime of omega. And d of omega are the test functions, and d prime is the prime here stands for dual space, yeah, and okay, distributions, this we call the test functions, And here's the definition. On an open subset of Rn, the space of distributions is defined as the vector space of linear maps which are continuous with respect to the seminorms. And this means that for each k, please take this as a definition, yeah, for the continuity with this family of seminorms. So for each compact set k of omega, there exist finitely many indices and constants, such that the following inequality holds for all test functions with compact support in k. Yeah, we can bound the absolute value of the map f on phi by the map f by this linear combination of these seminorms. Okay, where we have finitely many multi-index. The multi-index can of course be also 0. Yeah, and okay, let's check for an L1 function whether this is really obeys this. Yeah, so for f in L1 local of omega. So what does this mean, local? It is for every x of omega there exists a neighborhood, an open neighborhood O of x such that the restriction of O belongs to L1 of O. This means locally. Yeah. Of course, neighborhood in omega. Okay, then for any such function, yeah, the map phi going to integral f phi d mu is continuous in this sense. Okay, let us prove this. Yeah, let us prove this. Also, so let k be a subset of omega and be compact. Okay, then we can cover k by finitely many O1 bis OL contains k such that sorry, maybe we call this capital L, such that f restricted to OL belongs to L1 OL for L equal 1 to capital L. Now this follows, since this is this follows since f belongs to L1. Yeah, because f belongs to L1 local of omega. Okay, and this clearly implies that f restricted to k belongs to L1 of k. yeah, since we can estimate the, yeah, with the f with the L1 norm of k is clearly smaller than the sum of this L1 norm. Sum L equals 1 to L of f restricted to OL norms, L1 of OL norms. Okay. Here we also restrict. Yeah. Clearly, since this covers k, we have this estimate, so the L1 norm is bounded, so it's really an L1 function. Yeah. And then we obtain the following: integral f phi d mu is smaller, yeah, by Hölder's inequality, is of course smaller than phi, the supremum norm, times integral f d mu over k, and this is yeah, and here we can insert k0 times f restricted to k L1 norm of k. So this is a finite number, so we have proven that this inequality is in fact true. Yeah, this is the constant here. Sorry, this corresponds to C1, and alpha 1 is 0, and we have only 1. Okay, so we have many examples. All local L1 functions define as such distributions. Now we define the support, yeah, as the complement of all subsets omega, such that V vanishes on all test functions whose support is contained in omega. Yeah, we take the union of all such subsets O, and then the complement of this union. This is the support of the distribution of the distribution F. Now clearly there exists test functions which have support in a closed ball. Here we define this. And you see, if x, this exponent, since this is smaller than 1, this is always negative. And when x approaches, the absolute value of x approaches 1, then this goes to minus infinity. So this goes to 0, and this goes to 0 then faster than every power, so this is really a smooth function. Phi, this function is smooth. You should know this. I guess you have seen such constructions before. So we see, now we give an argument why, at least for continuous functions, the map, also for continuous functions, the map C of omega going to d prime of omega, which maps F to the corresponding distribution with, where we define this distribution as we note it's before, is defined by phi going to integral f phi d mu. Yeah, every continuous function is clearly locally in L1, so we know that this is well defined. So, and now we claim the map is injective. Yeah, so this means for if we have two continuous functions, then which are different, then the corresponding distributions are also different. So this means we can indeed distinguish all continuous functions by these distributions. Okay, why this is the case? Since this map is linear, it suffices to show that the kernel is trivial. So let's assume if f is not identically 0, then there exists x in omega with f on x absolute value is non-zero. Okay. Let epsilon be smaller than f of x absolute value. Yeah. Then there exists. Also if the value is non-zero, yeah, since we consider real functions, also we either have f of x is larger than 0 or f of x is smaller than 0. Yeah? In the first case, there exists delta larger 0 such that by continuity f restricted to the delta ball is contained in the set epsilon infinity, and in the second case f restricted to the delta ball is contained in minus infinity minus epsilon. Yeah, because this is a neighborhood of f on x. Yeah, this is a neighborhood of f on x, so by continuity there exists a neighborhood. In particular, there exists an open ball. Yeah. Now, by rescaling this function, there exists phi in C0 infinity omega with support of phi contained with support of phi contained in the delta ball. Yeah? And phi is the delta ball. is the delta ball and is larger than 0. Okay, so such that restricted to the ball, it's really positive. And then we clearly have that the integral of f times phi d mu is absolute value, yeah, is larger than epsilon times integral of phi d mu, yeah, since, and this is not 0, so this is non-zero. Yeah, so we have indeed f phi is non-zero. Yeah, as the linear corresponding linear map is non-zero. Yeah, so the kernel of this linear map indeed contains only functions which vanish identically. Yeah, since whenever the function is at some point non-zero, then this is non-zero. Yeah, so this proves the claim. Okay, now let's give us a simple example, and the simplest example is called the delta distribution. Yeah, and it just maps phi to the value of at 0. Yeah. Also hier omega should contain 0, of course, yeah, such that this is well defined, yeah, such that this value is well defined. Okay, this is a simple example, but it's rather clear that this example does not correspond to a function. Delta does not correspond to a function. Yeah, why not? The corresponding function, yeah, if you want that, also if we want to have phi d mu is equal of phi of 0 for all phi in, yeah, this would mean the support of f should be contained only in the point 0. It should be only one point. And the integral over f d mu should be 1. Yeah, but a function which only, since 0 has measure 0, there cannot exist such Lebesgue, at least Lebesgue integrable functions do not exist in this way. Yeah, so as a measurable function, it's impossible. Yeah, so this is not really a function. Okay, but we shall see that that we can approximate this by functions, even by smooth functions. Yeah, this we will see later. Okay, the disadvantage in general, we cannot multiply distributions with each other. Yeah, this can be considered as the price we have to pay for our generalization. But we can multiply distributions with these test functions. Yeah, so with these smooth functions with compact support. yeah, or even with it's a little bit more general with smooth functions. Yeah, and how we do this, GF of omega going to R, and this maps phi to G phi, F of G phi. Yeah, if F is from the form above, yeah, which we defined here, then we see G times, yeah, of phi. This is of course integral of F times G times phi d mu. So this is the same as F times G F. Yeah, in this sense, this is the natural way how to define the product with a smooth function. Yeah, and of course, if we multiply a smooth function with compact support, then this is also a smooth function with compact support. Also for all G in C infinity, we have the map G dot, which maps test functions to test functions phi to G phi. Yeah, and this again, of course, has compact support and is smooth, and clearly, yeah, it is continuous. Is continuous with respect to the seminorms. Yeah, since the derivative by the Leibniz rule, we can estimate the derivative here in terms of this derivative. Okay, so this is continuous. Now what we want to do now? Now we want there exists another product. Yeah, on the smooth functions there exists another product. Convolution. Convolution is another product on the space of functions. Yeah, how is convolution defined? Also, if you haven't seen it, we define it now. The convolutions of two functions, it's denoted by star. It's defined as an integral over Rn. First we define it for functions. The n of y, and by the invariance of the Lebesgue measure, yeah, we may substitute x minus y. So this is the same as g of z. Yeah, and if we substitute z is equal x minus y, yeah, then clearly y is x minus z. So we get f times f of x minus z. Yeah, and by the translation invariance, the measure with respect to y is the same as by this substitution. Yeah, since Lebesgue measure is translation invariant. Yeah, and of course, if we multiply it by -1 by Jacobi's transformation formula, it also doesn't change. So we have this formula. Yeah, so you see this formula. So this is, so we have G times convolution with F is the same as F convolution with G. Yeah, because here, if we interchange the role of G and F here, then we obtain this. And by the substitution, we say that these are equal. So it's indeed another product, and it's also abelian. Yeah, this is another product, and it's also abelian. And it's associative, commutative and associative. Now we want to extend this product to a product of a smooth function and a distribution. And now we want to extend. So let's calculate here. Also, let's do this calculation here. Yeah, here we just define f times g f d mu. I omit here the, okay. So this is integral phi of x, and now we have to insert here this formula. So we obtain times g of x minus y, f of y, and then of course first integral y such that we elevate this, and then integral x. Okay, this we can also write. Yeah, now we write this. Also now we use write this differently. We just abbreviate this and write this as phi of x times integral, and then we write this, denote, we define this in a moment. These are two operators of y times f of y. Also hier Tx is defined C0 infinity omega to, we translate the functions, so it's also translated phi maps to Tx phi, and Tx phi, yeah, of y is defined by phi of y minus x. Yeah, here is a minus and here is a plus. Please observe this. Here is a minus and here is a plus. Yeah, if this function does not vanish at a point z, yeah, let's assume phi of z is non-zero. Yeah, then this means then y minus x is equal to z. So the point y is equal to z plus x. So you see, indeed, we add to the points in the support of phi, we add x, yeah, to obtain the support of this function. Yeah. Okay, so we have this map, and this is also clearly continuous. And we also have this other map, P, C0 infinity of omega maps to see test functions on minus omega. These are, of course, the new domain where which consists of those values whose negative belong to omega. Yeah, phi maps to p phi, and p phi of x is just phi of minus x. Okay, now let's look at this. So we first reverse. Yeah, we first reverse. So let's do the calculation. Yeah, we need this. TXP G of Y. What comes out? Yeah. Okay, we first take P. So this is Tx of Pg of Y. And this is now Pg, we should take the negative. So this is G. Now we should take the negative minus, and now we should translate. Yeah, so we should translate. Yeah, this means y minus x, and this is g of x minus y. Yeah, and so you see this is exactly the same. Yeah, this is easy. Yeah, it's just another way to write this. And then we have another formula, and then we claim this is also equal to, yeah, so let's explain the second formula, integral phi g convolution with f dnx, this is equal integral over, we reverse the order, we use Fubini. Yeah, here we use Fubini. So we have phi of x and g of x minus y times f of y. Yeah, and here we use that we may reverse the order, yeah, because this product is clearly L1, yeah, because compact supports smooth and so on. And F, yeah, okay, F, when F is, for example, L1. Okay, and now we can write this as an integral over phi convolution with PG f d and y. Y is this, yeah, let's calculate. What is phi convolution with G, with PG? PG of y. What is this? Yeah, this is of course, yeah, now we use, this is phi of x times g of minus, since we have PG minus, and then we have y minus x, y minus x, yeah, y minus x. Yeah, and this is of course integral phi of x times g of x minus y dx. Yeah, and here you see, this is exactly the inner integral. F doesn't depend on x, so we can put it out. So we indeed have this formula. Okay, so we have two formulas. First, this is equal to this, and second, this is equal to this. Now we may use this to define the convolution, yeah, Therefore, G convolution with f is now a function. It's not a convolution, it's a function. And the function is just defined as the value of the distribution on the translated function Pg. Yeah, okay. G is a test function, Pg is a test function, translated is a test function, so we may evaluate this. So this should be well defined. Okay, why this is the case? Yeah, how comes this formula? Yeah, look at this expression here. If we evaluate this on the test function phi, yeah, then we get this integral. But this integral is just the distribution corresponding to f evaluated on this test function here. Yeah, this is this function evaluated on this test function. Yeah. So this formula here shows indeed that this distribution corresponds to this function, x going to this expression here, this integral, which is exactly this, yeah, if f corresponds to the distribution f. Okay, so this first formula explains the first formula, or second possibility, we define it now as a distribution, not as a function. Sorry, but we do it globally, yeah, in order to avoid this change. And phi maps to this maps to f of phi Pg. And this is exactly this formula. Yeah? If you look at this formula, if the distribution, if f is if the distribution capital F corresponds to the function, then we have to evaluate here. So this is exactly this formula. Okay, now we can put this to a lemma. Yeah. So now we summarize and prove this. The convolution of a distribution with a test function with compact support is a distribution which corresponds to a smooth function, namely to this function. Yeah, the support of this distribution is contained in the pointwise sum of the supports of the function and the distribution. Okay, how this comes? Yeah, we need to show that this is a smooth function. Yeah, yeah, we understood this is the function. So proof. It suffices to show, as we have to show that x going over to f of tx pg is smooth. Okay, and there we do this calculation. Yeah, if Pg is of course again a test function, so it's enough to show that x going over to tx, yeah, is that we can take the derivative. Yeah, and of course if we let us call it here a, also for some vector, any vector minus t epsilon limit epsilon goes to 0. This is of course ty t epsilon h minus 1. Yeah, because if we translate first by y and then by epsilon h, then we translate by y plus epsilon h. Yeah, and here we only translate by y times epsilon. Yeah, and this is the differential, the quotient which defines the differential. So limit epsilon goes to 0, and this is clearly the sum over hi di. Yeah, because this converges here, yeah, to the derivative. The derivative in direction of h. Yeah, this converges to the derivative in direction of h. So we obtain this. Yeah, and clearly this converges in the sense of these distributions. Yeah, because the distributions are smooth functions, and by the supremum norm, since this is invariant by translations, yeah, we have this. Yeah, so this is indeed, this shows indeed that this is now a smooth function. Yeah, because we can take derivatives just by taking the derivatives of the function g. Yeah, okay, or pg. And so it's a smooth function, and yeah, we can, of course, we can take also higher derivatives. Now we can repeat the same procedure for these derivatives, and since g is smooth, also this is smooth, and so this is in fact a smooth function. Yeah, now comes only the statement with the support. Yeah, this only does not vanish. It's on a neighborhood of point x such that this is true. Yeah. For an element y in support of y. Yeah. So we see indeed that the support is, this proves this statement about the support. Okay, so this lemma implies that even the convolution of a distribution with compact support is a well-defined distribution. Yeah? Namely, we do this. Yeah, of course, if g is not a function but a distribution, then we can do this. But then this has compact support if the distribution g has compact support. So this is now a smooth function of compact support. So this is well defined. So indeed we can define this. Yeah, and clearly, yeah, here we should use this definition. In particular, yeah, the delta distribution is, since the delta distribution, yeah, maybe we show this delta distribution f, yeah, or if we also here, if f is the delta distribution, yeah, so g convolution with the delta distribution, then we should take the value at 0. Yeah. So let's do the calculation. G delta distribution. Now we do it here as by evaluating this. Yeah, this is now phi maps to, and then we obtain the value so we obtain delta of phi phi with PG. Okay. This we already calculated here, so we should evaluate this at 0. If y is 0, yeah, what we get? We get integral of phi of x times g of x dn en x, and this is of course the distribution fg of phi. Yeah, and if we do it as a function, yeah, if we do it as a function, g delta as a function, then it's the function x going over 2, and now we should evaluate this. We should evaluate this delta of tx pg, yeah, tx pg, where we did this here. Now we should insert y equals 0. Yeah? So this is g of x. Yeah, we should insert y. So it's really the function g. So convolution with the delta distribution doesn't change. So this is the neutral element of the product of the convolution. With delta distribution does not change. Okay, here we stop. Let's recall what we have done. Yeah, we introduced the distributions as generalized functions. We introduced how to differentiate them. We showed that we introduced some continuity. We need some continuity. And we showed that the distributions uniquely determine continuous functions. We introduced one example, the delta distribution, which is not a function. We understood that we cannot in general multiply distributions with distributions as we multiplied functions, but we can multiply a distribution with a smooth function. And then we introduced another product type, namely the convolution, and understood that a smooth function with a distribution, that a convolution of a smooth function with a distribution is well defined and is a function, and that we can consider this either as a function or distribution, and that if we have a distribution with compact support, then we can even define the convolution of distributions. Okay, thank you. And that the delta distribution is the neutral element of this new product. Thank you.